Yeah, thank you, Massimo. And I want to thank the organizers for this invitation. And as the title indicates, I'm going to be talking about suspensions of microscopic swimmers. But the swimmers are not spherical. And I'm going to talk about two problems. Roughly, the talk is divided into two halves, although I don't do it explicitly. The first has to do with shear-induced migration. And the second has to do with what shear-induced migration has to do with dispersal of the microbial or microswimmer population. So in other words, the rate of spread of the population. So this is predominantly work done by a former postdoc, Dr. Lakshmi Narasimha Rao, who is now an assistant professor elsewhere in Geetham University, Hyderabad. And the simulations, a couple of the slides show simulations, results from simulations. They've been done by Sankar Nambiar, who was a former PhD student and who's now postdocing in Noida. Okay. So I want to begin by showing these two pictures of experiments, both of which have to do with shear-induced migration. And in fact, the right-hand side picture was dealt with by both speakers this morning, particularly the last talk. And that has to do with the migration of an active swimmer, clammy, which is gyrotactic. And this is sort of a classical experiment by Johann Kessler, who showed how the balance of gyrotactic and viscous torques leads to the algae preferentially sampling the downwelling region in a laminar flow, okay? And relatively speaking, downwelling. And I think this effect has been observed even in more complex turbulent flows. So this is, one could say, a classical example of activity-induced shear migration. And the left-hand side picture is actually even older. It has to do with an experiment done by Andreas Akrivos and his PhD student, Gadala Maria, Francis Gadala Maria. And it was published, I think, in Journal of Rheology 1980. And it has to do with migration of passive spheres. So shear-induced migration was, in fact, has a passive origin and passive suspension mechanics. And you can see what's plotted is the relative viscosity versus time, where the viscosity undergoes a gradual decrease with time. Okay? And notice that it's very gradual. The time scale is of the order of hours. Okay? And the viscosity decreased because the authors finally found out that the spheres were migrating from the high shear region, which is the gap in their experimental Couette device, to the low shear region beneath the Couette cylinder. Okay? Now, shear-induced migration in active suspensions has been attracting a lot of attention, and this slide sort of contains a summary of all the many of the experiments. Okay, so we have migration being dealt with in simple rectilinear shearing flows. Okay, in curvilinear shearing flows, for instance, that induced by a rotating particle, that induced in a cavity sort of geometry with a large-scale vortex in it. And there have been experiments in nonlinear rectilinear shearing flows where Roman-Stocker loop shown that you can have a trapping of gyrotactic particles in a thin layer in the high shear region. And more recently, you've had complex laminar flows. People are starting to look at the pore residence distribution times of swimmers in both in natural and model porous media. And of course, you have swimmers in turbulence, which was the topic of the previous speaker. And here I'm showing just one experiment cum simulation, which shows the patchy distribution of gyrotactic organisms in turbulence. But what I'm going to be focusing on are these experiments that have been done by Roman-Stocker's group. And in fact, they had to do with the simplest of the shearing flows that are in the slide. It's just pressure-driven channel flow. Okay, and the complication here doesn't come from the flow. It actually comes from the shape of the swimmer. So you could say that of all these experiments, the swimmers were treated as having a spherical geometry at that time. And so the complication was in the gyrotactic torque interacting with the viscous shear torque acting on a spherical particle. But it's these experiments that first convey the non-trivial selective nature of the shape. And that's what my focus will be on. So let me just tell you a little bit more in detail about these experiments. Okay? So the first experiment was done in this configuration. It was essentially a microfluidic channel. And you can see that the aspect ratio of the cross-section was sufficiently high that you could approximate the pressure-driven flow to be a plane Poiseuille flow. And what the authors observe is shown in these snapshots here. So the black dots correspond to actual bacteria. Okay? And the leftmost plot shows dead bacteria. And the vertical coordinate is the gradient coordinate in the channel geometry. So what the leftmost plot shows you is that the bacteria went dead. So the bacteria used here was Bacillus subtilis. So dead bacteria tend to uniformly distribute themselves across the channel cross-section. But when the authors considered swimming bacteria, then they noticed that there is a depletion close to the center line. So bacteria preferentially migrate towards the walls. Okay? And interestingly, they plotted a measure of what they call the depletion index, which is just a dimensionless measure of the degree of inhomogeneity. And they showed that the degree of inhomogeneity turned out to be maximum at a finite shear rate. So the horizontal axis is the shear rate. The depletion increased and then seemed to go back to zero when the shear rate became very high, of the order of about 50 per second. Now, so this one would call this as a high shear trapping because bacteria migrate towards the walls. Okay? Now, a second experiment done in the same apparatus with a variety of algae seemed to suggest something more interesting, because two of the algae, the one on the left-hand side column, seemed to exhibit a depletion from the center and accumulation of the walls. But there were two other algae, actually the biflagellated ones, which seemed to accumulate at the center. Okay, and so there was high shear trapping and a low shear trapping. And in fact, they found that if you plot the depletion index, and if you look at the green curve here, the green curve initially is positive, okay, and then changes sign to become negative. So that would imply that there is a transition from a high shear trapping to a low shear trapping regime with an increasing shear rate. Okay? Now, the high shear trapping was explained earlier, and it's intuitive. The low shear trapping wasn't clear at the time, and this is what we first found. And I'm just going to talk about that for a little bit. So the elementary swimmer here was Bacillus subtilis and the algae in the other experiment. Now, both can be modeled via a standard model for the microscopic dynamics, which is called the run and tumble motion. So bacteria certainly execute run and tumble dynamics, and many of the algae also do. So what that involves is the swimmer running along a straight line for a given period of time. Okay? But then periodically for a bacteria, the flagellar bundle that propels the bacterium comes loose. Okay? And therefore it wiggles for a while without going in any net direction. And that event is called a tumble. And then the bundle comes together in a different orientation, and it sets about running along a different direction. Okay, so basically this leads to a random walk. There is sort of some correlation between run one and successive runs, but that correlation is gradually lost over many runs, and eventually, in the absence of a flow, the swimmer samples its environment diffusively. That diffusion coefficient scales with the square of the swimming velocity times the decorrelation time. So the decorrelation can, as I just said, either happen rather suddenly or impulsively via tumbles, or as is the case for synthetic swimmers, it can occur via a rotational Brownian motion, okay? Not necessarily thermal, but rotational fluctuations, smooth, small amplitude orientation fluctuations. Okay? And that sort of leads to two classes of swimmers, which are typically known as run and tumble particles and active Brownian particles, so RTPs and ABPs. Okay? So the equation that one starts from, and this is one of very few slides which will contain equations. I just have to tell you what the model was. So this is the kinetic equation governing the bacterium probability density. Okay? And the key thing is that the orientation of the bacterium is crucial, because remember, we are seeking to model anisotropic bacteria, not spherical swimmer, for which these effects are absent, the ones that you saw in the experiments. And so the swimmer probability density here, omega, is a function of both position and orientation degrees of freedom. Okay? So the swimmer probability density evolves due to the two decorrelation mechanisms that I mentioned. One is rotary diffusion, which is this Laplacian in orientation space, and the other is tumbling, okay, which is this integral term here. Okay. And then the orientation distribution also is convected by the swimming motion. And finally, the orientation of the swimmer is rotated by the imposed shear flow. Okay. Now, it's via the shear flow that the shape of the bacterium enters, because that's governed by the Jeffrey equation. Okay. And R here is the aspect ratio of the bacterium. Okay. So when you have a spherical swimmer, R is 1. And P dot just is proportional to the vorticity. So spherical swimmers rotate at a uniform rate and always have an isotropic orientation distribution. Okay? Whereas the orientation distribution can be biased in certain directions when the shape of the swimmer departs from unity. Okay? Now, this equation essentially treats a swimmer as an equivalent spheroid. Okay? So R is the aspect ratio of the spheroid. And what I'm showing here is a slender prolate spheroid with a certain orientation, P. Okay, we look at the opposite end of the spectrum, oblate spheroids too. Okay, so the shape is modeled as a spheroid, which is the best we can do here. And at least it has been shown that provided the geometry is axisymmetric, the spheroid is not restrictive. Most axisymmetric particles behave like equivalent spheroids. So if you just break the problem out into the number of dimensionless parameters, okay, then you have what one might term the bacterial Knudsen number, which is, it's called the Knudsen number because it's the ratio of a microscopic scale, the elementary swim mean free path, to the macroscopic geometry, which is the channel thickness. Okay. Then you have a measure of the strength of the flow, which is the rotational Peclet number, the gradient of the velocity, imposed velocity, times microscopic time scale, the bacterium shape, that's the aspect ratio, and a parameter that tells you how important tumbling are and rotational orientation fluctuations are in terms of randomizing the bacterium orientation. And so accordingly, as I said, for two extremes, you have the ABPs and the RTPs. So now it turns out we don't need to deal with all four parameters because the experiments, the Knudsen number was fairly small. Okay, epsilon was 0.23, and actually it looks worse than it is. The assumption gets better at higher shear rates. But if you make the assumption that the bacteria Knudsen number is very small, then you can sort of separate timescales and say that the orientation relaxes on a very fast time scale. And then the spatial dynamics is governed by, you can integrate out the orientation degrees of freedom and arrive at what is written here, just a simple drift diffusion equation. So dyy here, y being the gradient coordinate, is the gradient component of the diffusivity, and v here is the gradient component of the drift. Okay, and at steady state, you have a very simple concentration profile that's just related to the ratio of the drift to the diffusivity. Okay. And note that both the drift and the diffusivity depend on the swimmer aspect ratio and the Peclet number. So that's where the shape dependence and the strength of the flow come into play. So we started out looking at infinitely slender swimmers, and this is something that it turned out had been looked at by earlier theoretical efforts also, that of Rachel Beeran, who's a speaker at this conference, and David Saint-Jean. And we found overall consistency with the experiments as far as the concentration profile is concerned. So what's plotted on the left-hand side is just the concentration profile, a bunch of concentration profiles as Peclet increases from small to large values of order 1,000. So at the smallest values, the concentration profile is practically uniform. And as the shear increases, as the Peclet increases, then you have a dip at the center. Okay? And asymptotically, as Peclet goes to infinity, you observe that there is a Peclet independent profile with a cusp at the center line that's been set up. That's denoted by that orange dashed line here. Okay. Now that cusp is not really a cusp, it's an artifact of our analysis. So remember that the analysis is not valid on scales of the swimmer mean free path. So here the singularity will be broken up by the finite swimmer mean free path. But nevertheless, we were predicting a near center depletion just as observed in the experiments. And so when we plotted the depletion index, we observed for the first time there is something different from the experiments, the first set of experiments, because our depletion index had a mild non-monotonicity, but it went to a Peclet independent limit for Peclet going to infinity. Okay, and that has to do with this orange dashed line, which is the infinite Peclet profile, being independent. Okay, and that in turn has to do with the fact that both the drift and the diffusivities, as I show at the bottom, scale with Peclet in the same manner. They become small. Okay, both of them decrease as the -4/3 power of Peclet, but since they scale the same way, the concentration profile itself is independent of Peclet. Okay, so the idea was, given enough time, there isn't really an optimal shear if you ignore the small maximum. You might as well shear it at much higher shear rates, and you will practically obtain the same depletion. Okay, so this stood in contrast to the large non-monotonicity in the experiments, and we think that the problem was that the residence time in the experiments wasn't long enough, because the evolution time for the concentration profile becomes longer and longer as Peclet goes to larger and larger values. Okay? But the unexpected thing came when we relaxed the assumption of an infinite aspect ratio. Okay? So when we went to finite aspect ratios, okay? And that's here. So this aspect ratio is 1.25. Then you can see again the same sort of a plot, concentration profiles versus Peclet. And this bunch of profiles here that I'm pointing to here denote the low Peclet set, okay, where Peclet increases from 0.1. So you again have a nearly horizontal profile at 0 Peclet. And then there is the usual, there was the expected development of a near center depletion. But then as when you increase the Peclet further, the near center depletion actually became a near center excess. And as Peclet increased for this aspect ratio, you approached again a Peclet independent profile, but a profile that was directed the opposite way. So in other words, the swimmers actually accumulated at the center rather than being depleted at the center. And the infinite Peclet profile was again finite, because it turned out that the drift and the diffusivity again scaled with Peclet in the same manner, except with a different power of Peclet. Okay? Now, these scalings are, in fact, you can anticipate them. I won't go into any detail, but based on work done by John Hinch and Lillo in the 1970s with regard to the orientation dynamics of anisotropic particles. So it turns out that they have a non-trivial consequence for active particles. So as you can see that this reversal and shear-induced migration led to the depletion index changing sign on the right-hand side. So it started off one sign, which indicated a near center depletion, but then changed sign and then asymptoted to a Peclet independent value, because as I already said, the ratio of the drift to diffusivity decides the Peclet dependence of the concentration profile. So then after seeing this, it seemed like the reversal in the second set of experiments was also explained. And then we decided to do different aspect ratios. And it turned out that whatever happened for 1.25 happened for all other finite aspect ratio. It's just that the threshold Peclet at which that reversal and migration happens starts increasing with increasing aspect ratio. And you'll see that here, as I go through these four profiles in the clockwise sense, the aspect ratio is increasing from 1.25 to I think 2, then 4, and then 8. Okay? And you can see that the largest Peclet corresponds to an increasingly blunt profile as I go to higher aspect ratio, implying that the reversal in migration hasn't fully developed, and there is still some way to go. And that's because the migration happened later at a larger Peclet. So you have to go to a still larger Peclet in order for the migration to be fully developed and for you to get the asymptotic profile with the cusp. Okay, and the Peclet at which this reversal happens scales like the cube of the aspect ratio. So it's not small. And this is again something that can be anticipated based on orientation dynamics of passive particles. Now, the one thing, immediate advantage when you recognize this is that you can engineer a phase diagram to map the high shear and low shear trapping regimes. Okay? So the idea is that you have a parameter plane, the horizontal axis is Peclet, the vertical axis is kappa. Okay? And for any fixed kappa, as you increase the shear rate, which means Peclet increases, you move along a horizontal line. You move from the high shear trapping regime here, which are denoted by the red symbols, okay, to the low shear trapping regime. Okay, and therefore you can, if you have enough of these points, you can loosely draw a boundary between the high shear and low shear trapping regimes. Okay, and that's a good thing. For one thing, you can separate swimmers based on shape, because at a given flow rate, swimmer of a given aspect ratio might migrate towards the center, but one with a higher aspect ratio might migrate towards the wall. And if you have differential migration, then you can obviously engineer a separation protocol. Okay, so now it turns out this swimmer state diagram or shear-induced migration diagram is also consistent with the experimental results that we could extract from the Stalker articles. You can see that the blue triangle here denotes low shear migration, okay, and which is consistent. It lies on the right side of the boundary. Okay. So this is, we had modeled the swimmers as active Brownian particles. Okay, so tau dr is infinite. So there is, the tumble time is infinite. They don't tumble, they instead rotary diffuse. Now you can also calculate a phase diagram in an identical manner for run and tumble particles. Okay? And you can see that the physics is identical. In both cases, there is a transition from high shear to low shear trapping as Peclet increases for a given swimmer shape. Okay, but the shape of the boundaries are very different. In fact, you can argue that the shape for RTP, Peclet should scale linearly with kappa along the boundary, and it should scale with the cube of kappa for ABBs. Okay, and an interesting thing that emerges as a consequence of this dependence is the fact that you can have a separation protocol based on swimming characteristics. So the differing boundaries imply that if you superpose these two diagrams, there will be an overlapping region, so to speak, where RTPs go in one direction, but ABPs go in the other, and you can have, therefore, in principle, a separation based on swimming characteristics. So this is what I was pointing towards. Now, the one thing that we did after this was that we saw that marine phytoplankton tend to come in an extremely wide variety of shapes. And given our Jeffrey equation and the fact that we had looked at the entire range of aspect ratios from 1 to infinity that corresponds to prolate swimmers, we just decided to see what disc-shaped or oblate spheroids would do. Okay? So this is the idea. This is something that I just spoke about. And this is something that I'll just briefly describe in a couple of slides. So normally, if you are familiar with anisotropic particle dynamics, the oblate spheroids usually do the exact opposite for prolate spheroids. Okay, so this remains the governing equation, except note that R is greater than 1 for prolate spheroid swimmers, and R is less than 1 for oblate spheroid swimmers. Okay, so if we go by this intuition, then it seemed the first efforts that yes, the intuition was correct. Okay, so here on the left is a prolate spheroidal swimmer of aspect ratio 4, okay? And on the right is a disc with the aspect ratio being the reciprocal of that prolate spheroidal swimmer. Okay? And you can see that something that we have already seen for the prolate spheroid, there was an initial near center depletion that gradually became a near center excess due to a reversal in the direction of migration as Peclet increased. So you went from high shear trapping to low shear trapping with increasing Peclet. Okay, and oblate spheroids exhibit expectedly, perhaps, you went the opposite direction. So initially you had low shear trapping here, but as you increase Peclet, the profiles dipped down, implying that you went from low to high shear trapping with increasing Peclet. Now, then we went to what initially seemed like the simplest case, which is just take the aspect ratio to be infinity. Because remember, the infinitely slender swimmers that we considered exhibited only high shear trapping for prolate spheroids. So it was natural to contrast the infinitely slender rod with the infinitely thin disk on the right. Okay? And you can see the scalings for the drift and the diffusivity that I've given here. Okay? Now there's one crucial difference here. If you notice, for the infinitely slender rod swimmer, the drift and the diffusivity scale as the same power of Peclet. But for the oblate spheroid, the disk, they don't. The diffusivity actually becomes much larger than the drift, okay? Implying that the degree of inhomogeneity for the disk-shaped swimmers eventually is wiped out because the diffusion becomes much smaller than the inhomogenizing drift, okay? And as a result, if you plot the depletion index for these cases, okay, then the prolate spheroid depletion index, as we already saw, if you ignore that mild non-monotonicity, it just saturates at a finite value as Peclet goes to infinity. Whereas interestingly, the disk-shaped swimmer exhibits the maximum inhomogeneity at a finite Peclet. Okay, so there's a little bit of an irony in that the original and interesting prediction of a critical shear rate corresponding to maximum inhomogeneity came for rod-shaped swimmers in the experiments, which, as I said, was likely an artifact. But it turns out that disk-shaped swimmers for sufficiently thin disks truly exhibit a finite Peclet maximum as far as the inhomogeneity is concerned. Okay. So that sort of brings me to the completion of the first part of my talk. And for the second part, like I said,
Ganesh, can I interrupt you a moment?
Please.
No, I wanted just to point out, I mean, just a comment. I mean, it's very interesting what you presented. That recently there was a paper, which I will post on the chat for everybody, maybe would be of interest, by Berman and collaborators, which has been published on Frontiers in Physics, in which very similar results to yours were shown, but obtained with a different approach. I mean, they worked out a different, let's say, multiscale, stochastic multiscale approach on the stochastic part, the rotational, the diffusion, the dynamics, and then they exploited a lot of ideas from dynamical systems. But I mean, the results seem to me consistent with what you have shown. I mean, it was just a comment. I mean, just to.
So the physical problem is still identical. That's what you're saying.
Yeah, they were looking actually to a different flow. Is a Kolmogorov flow. I mean, but you can imagine as a Poiseuille flow. I mean, without
reversed periodically.
Two Poiseuille flow in different directions, if you want.
Correct.
And the dynamics is the same. I mean, just Jeffrey dynamic for the orientation and different aspect ratio from disk to rods. I mean,
right.
I mean, just wanted to point out this to.
Thank you. I'll certainly have a look. Okay, but you could send it to me if you can. So,
sure. I will send you a couple of references on this. Okay? Sure.
Okay. But if there are any more questions, I could take them at this point before I proceed to the second part.
Yeah, I have a naive question. Sorry, but naive question. But maybe many others know the answer, but I don't know. Is there some limit here where we can just do a simple mapping of normal Taylor dispersion by using an effective diffusion coefficient or something, or is there nothing? And why is
that's precisely what I'm coming to. So that's what the second part of the talk deals with. So that Taylor dispersion has to do with spread in the axial direction. So I just spoke about the distribution along the transverse direction, and I'll talk about how it might be coupled to the axial evolution. So perhaps I might be answering your question over the next few minutes. Does that make sense?
Perfect, thanks.
Okay, so maybe I'll proceed. So like I said a couple of times before, we have looked at the swimmer dynamics along the gradient direction, okay? The way they sample the velocity fluctuations as they migrate from the wall towards the center or vice versa. And the natural thing to ask is, does this influence the spread of the microbial population? This is a natural question to ask. And Poiseuille flow was in fact the geometry where this question was first asked by Taylor in the passive case. Okay? So this is just a summary of what I spoke about. So the key thing is highlighted in blue, in bold. There appears to be a crucial asymmetry between disks and rods. Okay? So anyway, so this is the question that we are going to ask. So if we have an initially localized population of swimmers that have, you can imagine, have equilibrated along the gradient direction in the manner that I just spoke about in part 1, what does it imply for the spread of the population in the axial direction, okay, along the flow direction? And like I said, this is the classical Taylor dispersion or axial dispersion problem. And we could forget swimmers for a moment and replace the swimmers by a passive solute. And we could talk about an axially localized slug as to how it evolves. And the answer was first found by Taylor, the fact that it evolves into a diffusively spreading Gaussian profile, the cross-sectionally average profile, which is what makes sense for long time because the solute has sampled all possible locations along the transverse direction. So he found that the Gaussian profile spread with an effective diffusivity, and this effective diffusivity was calculated by Taylor and later Aris with the addition of the bare solute diffusivity, and it turned out to be this. Okay, so the axial diffusivity is the bare diffusivity times 1 plus Peclet squared by 48. And notice that I've used the subscript T here. So this is the translational Peclet number, the usual Peclet number that appears in, for instance, in the chemical engineering literature. You have a velocity times a length scale, in this case, the radius of the pipe, divided by the solute diffusivity, which in this case can be regarded as being thermal in origin. Okay? And the non-trivial aspect here is that the axial diffusivity is enhanced, okay? And the enhancement is square of the Peclet number. So faster the flow, the greater is the rate of spread of this Gaussian profile as you go downstream. Okay? And you can do the same problem for plane Poiseuille, which is the one relevant in our case. And this was done at a later date, and this is the answer. So apart from the numerical prefactor, the physics is identical. So the axial dispersion scales as Peclet squared times the molecular diffusivity. Okay? And this is counterintuitive because you see, if you put together, if you write the actual contribution, in other words, multiply the Peclet squared by that diffusivity, you realize that the effective diffusivity is scaling inversely as the original diffusivity. So smaller the original solute diffusivity, the more rapid is the axial dispersion because the greater is the effective diffusivity. Okay, and this arises from the fact that when the diffusivity is smaller, then before the solute decorrelates, as the solute goes in the transverse direction. Okay, remember the diffusivity is gotten smaller. So as the solute goes in the transverse direction at a slower rate, it executes a larger step in the flow direction because it's being convected by a stronger flow, relatively speaking. Okay, and therefore there is a larger random step that it takes, and that eventually contributes to a larger effective diffusivity. So one way of arguing this out is to imagine that there is a single solute particle that starts from the center line, and its variance in the gradient direction, note that the gradient coordinate here I've denoted as z, increases in the usual diffusive manner, but at the same time, it's being convected along the z direction with a quadratic flow proportional to z squared. And now if you use averages, then the mean square displacement in the x direction turns out to scale with z power 4. And because z power 4 scales like t squared, okay, the mean square displacement will actually grow like t power 4 for short times, okay? And if it's an unbounded quadratic flow, the evolution along the axial direction will never be diffusive because the scaling will be with t power 4. But for a bounded flow, there comes a point which is a time scale of h squared by d, when the solute has sampled all the velocity fluctuations available. And that's when the t power 4 growth saturates, and it gives rise to a diffusive growth. And you can estimate that diffusive growth just by dividing t power 4 into a t cubed and a t. That t there contributes to the diffusive growth. This t cubed saturates at a time scale of order h squared by d. So if you put that together, you get precisely that axial diffusivity that I've written down here. Okay. So that's the answer for the passive case. And like I said, it's natural to inquire what happens for the active case. And the intuitive thing would be to do what I've done here. In other words, I've replaced the thermal diffusivity by the gradient direction diffusivity, which was the focus in part 1. So the intuitive thing would be if I replace the original thermal diffusivity by the swimmer diffusivity that's no longer thermal in origin, and as we saw can be dependent on Peclet, I will get the axial dispersion as a function of Peclet. Okay, so let me remind you that if I consider the scaling of dZz, the transverse diffusivity, for sufficiently large Peclet, for any swimmer aspect ratio, it scales as 1 by Peclet squared. Okay, so when as to how large Peclet must be does depend on the swimmer aspect ratio. So if the swimmer is fairly slender, then Peclet must exceed the threshold of order R cube for the diffusivity to start scaling like 1 by Peclet squared. Okay, now if you do that, okay, then it turns out that you will get, as you might guess, the effective diffusivity should scale like Peclet power 4. Okay, so for any finite aspect ratio, okay, for sufficiently large Peclet, the axial dispersion of a swimmer population must scale as Peclet power 4. It's even larger than the passive case, and that's simply because the diffusivity in the transverse direction has gotten smaller. It now scales like 1 by Peclet squared. Okay. For infinite aspect ratio, because the scaling is 4/3, you'll end up with a scaling of 10/3 rather than 4. Okay, but the idea is that the scalings, according to this argument, are immediately derivable, provided you know the scaling of the diffusivity in the transverse direction. So you might call this the classical scaling argument. And the idea here, over whatever content of the talk remains, is to see if this works. Okay. So let me just tell you that there is one subtle regime that I didn't speak about in the earlier case. And if you notice that I just told you for any finite aspect ratio, the diffusivity eventually scales like Peclet power 4. But that's not actually true. What's written here is that I have restricted the aspect ratios to values less than 2. So that's not finite. And that's because of something very interesting that we found in course of the shear-induced migration analysis, that if you let the aspect ratio be greater than 2, then all the swimmers within the framework of the multiple scales analysis collapse onto the center line. Okay, so the drift becomes so large compared to the diffusivity that all of the swimmers end up at the center line. So if you notice, this was the expression for the concentration profile. Okay, and here in the numerator you have the diffusivity drift, and at the denominator you have the diffusivity. So if you now take the infinite Peclet limit of the drift and the diffusivity, both scale the same manner with Peclet for rod-shaped swimmers. So the difference is, the ratio is independent of Peclet, but it is a function of the position inside the channel. Okay, and it turns out that that ratio is this. It's a constant K by Z. So in other words, the drift gets to be larger and larger as you come closer to the center line. Okay, and so if you put this functional form into that exponential, you get the concentration profile at infinite Peclet, okay, to be 1 by Z power C. Okay, and this immediately points to the fact that if C is greater than 1, then the profile is non-integrable. And the implication is that all of the swimmers have gone on to the center line when Peclet is infinite. Okay, and this is what I've termed the center line collapse at infinite Peclet. So this certainly appears to be a more complicated regime. Okay, because if all the swimmers lie arbitrarily close to the center line, the ability of a swimmer to sample velocity fluctuations along the gradient coordinate is hampered. Okay, so one could expect a different scaling for this case. So this is how the depletion index behaves. So on account of the centerline collapse, you see the uppermost curve there. So remember, the abscissa has 1 by Peclet. Okay, so as I go to the right extreme, the flow becomes arbitrarily weak. So I go to stronger and stronger flows as I move from the right to the left. Okay, now if I consider infinitely slender swimmers, then those swimmers follow that curve there, the blue curve. And you can see that the depletion index starts from a value that should be 0. So that 100 minus di is just 100 itself. And then saturates at a finite value as Peclet goes to infinite, implying that the concentration profile is finite, integrable, and independent of Peclet. Okay? But now as I consider finite aspect ratios, for aspect ratio 1.25, which is less than 2, I have the blue curve that is, loosely speaking, the mirror image of the original depletion curve for infinite aspect ratio. So in other words, again, I have a finite integrable concentration profile. It's just that it's an excess profile rather than a depletion profile, because we know that the migration reverses sign with increasing Peclet. But interestingly, if I go to aspect ratios 2 or larger, 2 appears to be very close to the threshold. Okay, you can see that the depletion index suddenly, not suddenly, but starts sharply decreasing as 1 by Peclet decreases or as the flow gets to be stronger. So in other words, the depletion index, the depth approaches 100, so that 100 minus di goes to 0. So you have almost perfect depletion from everywhere in the pipe, which implies all of the swimmers are right at the center line when the flow becomes infinitely strong. So I'm not going to go into the details of the argument, but if you summarize the classical picture, then based on what I just said, there are 3 ranges of aspect ratios to worry about. When the swimmer aspect ratio is less than 2, then I expect the classical argument to give me an axial diffusivity that scales like Peclet power 4. When I have an infinitely slender swimmer, then the axial diffusivity scales like Peclet power 10/3. Okay? Now the exponents are different, like I said, but they are expected provided only that you account for the Peclet scaling of the transverse diffusivity, which is why I term this the classical picture. For aspect ratios between 2 and infinity, you can sort of conjure up a scaling argument similar to what I used for the original Taylor's argument, Taylor result. And you get an result which is this 4 minus 8 alpha v. Here alpha v measures the rate of decay of the variance. What that means is that the variance decays algebraically as Peclet power minus alpha v, minus 2 alpha v, as Peclet goes to infinity. And that implies that the variance decreases to 0 for infinite Peclet, which is what happens when you have a centerline collapse. Okay. So given this, I want to now go into the actual results to see how much of this is true. Okay. So I'm not going to go into details of that scaling argument. Okay. I'm not going to give you details. The calculation is again based on a multiple scales analysis. Okay. Except that the fast time scale here in this analysis was the slow time scale of part 1. So in other words, the fast time scale is the transverse diffusion. The slow time scale is the longitudinal diffusion. Okay. And the final result that you get for an effective diffusivity, you get it in terms of the transverse diffusivity here, dZz, and the concentration profile, which I've denoted as f of t. U prime of x is the velocity fluctuation. So it's the actual velocity of the plane Poiseuille flow minus the concentration weighted velocity. Okay. So now the simplest case is to consider is spherical swimmers. Remember, spherical swimmers have an isotropic orientation distribution. So in this case, the concentration profile remains uniform. Okay. So it's sort of the closest to the passive case. The only difference is that the diffusivity of the spherical swimmer is still not a constant, unlike the solute. It decreases with Peclet, and therefore D effective still grows like Peclet power 4. In this case, you can predict the coefficient analytically. And that shows those results are computing that integral numerically. Okay? And that seems to match the predicted result. Now, the next is aspect ratios between 1 and 2. So first, I'm just showing you the plot of the concentration profile variance versus Peclet. Okay? And this is just to show you that when the aspect ratio is less than 2, the concentration profile variance, which is really the width of the concentration profile, asymptotes to a finite value as Peclet goes to infinity. So it just tells you that that finite value implies that there is no centerline collapse. Okay, so the profile is non-uniform, but the variance approaches a non-zero value in the limit of infinite Peclet. Okay, though that non-zero value, as you can see from these three plots, decreases as Peclet goes to, as the aspect ratio increases, because you're approaching that critical limit of 2. Okay? And another thing some of you might have noted is that the variance is non-monotonic. It first increases before decreasing. That's just the result of that shear-induced migration reversing direction. So when you have the swimmers moving towards the wall, the variance initially increases, the high shear trapping, and then they reverse and move towards the center, so it starts to decrease. So the transverse concentration profile is non-uniform, okay, but it's finite at every point. And therefore, the diffusivity, you can show that it still scales like Peclet power 4, albeit with a coefficient that is now no longer, you can extract it from the infinite Peclet concentration profile as a function of the gradient coordinate. Okay, and this plot here tells you that things are okay. So it plots the axial diffusivity versus Peclet for 3 different aspect ratios. And what I want you to just see is that all 3 fall on a line that increases, rises with a slope of 4, implying that the axial diffusivity increases with as Peclet power 4. Okay. Now I just want to go to the other end, right to infinitely slender swimmer, where we predicted a scaling of 10/3. Okay, and if you calculate that integral for an infinitely slender swimmer, again the numerical results support the scaling. So that's the blue curves, the numerics, and that grows with a slope of 10/3. Okay. So now when we come to aspect ratios between 2 and infinity, so as I've already told you, the concentration profile is non-integrable in this case, which implies points to a centerline collapse in the limit of Peclet going to infinity. So unlike the earlier case, the variance doesn't saturate as Peclet goes to infinity, it continually decreases. Okay, and so I can characterize its large Peclet form by this algebraically decaying form and see if it works. Okay, and that just tells you I have 5 aspect ratios here, aspect ratio increasing from 2.4 to 3.6. Okay. In each case, I'm plotting the concentration profile variance versus Peclet, and you can see that there is no plateauing behavior. Okay. They all decrease. And from the rate of decrease, I can extract what alpha V is. I just want you to note that alpha V is quite sensitive. The aspect ratio is not varying by much. I've just increased from 2.4 to 3.6, yet the variance exponent has significantly increased. Okay. Now, if I go to the axial dispersion curves, so again, this is the axial dispersion plotted versus Peclet for the same sequence of aspect ratios, 2.4 to 3.6. Okay. Now, for the leftmost, in the left-hand side top of my slide, you can see what I want you to focus on is the large Peclet behavior. That line actually turns out to be very close to a slope of 4. Okay? So that's because I'm still not very far away from the critical aspect ratio of 2. So that we'll see the exponent in a moment, but that's close to 4. But as you can see, when I go through in an anti-clockwise sense, there is an inflection that develops near the center of this curve. And the inflection develops because after the initial rise, the profile starts to rise more rapidly, but then turns over to a slower rate of rise here. And that rate there at the largest Peclet becomes slower and slower. So gradually that inflection becomes more and more prominent as the aspect ratio increases. So in other words, what I'm telling you is that the increase of the axial diffusivity with Peclet for the largest Peclets is becoming smaller and smaller. And you might have guessed that from an expression that I gave you earlier. So if I just go back a few slides, note that this was the expression that I told you worked for aspect ratios less than 2. And when r equals 2, the value of that exponent is 1, c. And you can see that the answer that the theory gives is 0, which implies that the exponent 4 is no longer valid. That answer is indicative of a crossover to an anomalously reduced dispersion. Okay, so the classical argument doesn't work. And so let me just, these are all these profiles plotted together. So all 5 aspect ratios, and this tells you that 2.4 increases very close to that red dashed line with a slope of 4. And by the time I reach 3.6, I'm growing at a significantly slower rate. So beta is just 2.05, and it's almost half of its value at 2.4. And it's interesting because remember, 2.05 is very close to the classical Brownian value of 2, which implies that if I go to aspect ratios greater than 3.6, and if I go to sufficiently large Peclet, there will be a regime where the original thermal diffusion might start to dominate the active component of the dispersion, okay, which grows with a smaller exponent. So this is for aspect ratios greater than 4. Now it becomes numerically more difficult because you have to go to larger and larger Peclets. And I'm just showing the onset of the anomalous regime here, where after the inflection, the axial diffusivity grows at a slower rate. And you can see that the slope becomes smaller and smaller, although you have to go to much larger Peclets here before you can ascertain that it's an algebraic asymptote. Okay, so you've just started to see the beginning of the anomalous diffusion for the largest aspect ratios. Okay, so one thing that I want to point out is that for the largest aspect ratios, which are 6 and 8 here, there is the emergence of an intermediate scaling regime where the diffusivity exhibits a scaling of 10/3, which remember was the scale for the infinite aspect ratio swimmer. So in other words, what happens as the swimmer aspect ratio increases is that the anomalous regime is postponed or delayed until an infinite Peclet, and the entire range of Peclets when the aspect ratio is infinite corresponds to a scaling of 10/3. Okay, now what I want you to note is that if I use the original variance-based argument, which gave me a value of 4 minus 8 alpha v, it doesn't work. Okay, so I haven't showed it here, but the eventual anomalous exponent isn't related to the variance of the profile, or at least not directly. And we were wondering as to what happens. And then we realized that the reason for this disagreement with the usual argument that gives you the Taylor result is the dominance of rare events or the tail events. And that's because the axial dispersion for swimmers of large aspect ratios greater than 2, that is, okay, is dominated by the small fraction of swimmers that actually move significantly away from the center line, even though the majority of the population is close to the center line, and in the process suffer large jumps. Okay, so there are 2 contributions to the variance here. One from the majority of the swimmers that are in the immediate vicinity of the center line for large Peclet, but that suffer very small jumps, and from the small fraction of the swimmers that are significantly away, but suffer large jumps. And it turns out that when R is greater than 2, you can use a scaling argument to show that that tail contribution actually dominates the core contribution. And it turns out that the exponent is the following. You can see that it's 4 minus c minus 1 times that variance exponent. And I want to remind you that c is greater than 1 when the aspect ratio exceeds 2, because the concentration profiles are no longer integrable, which means that that exponent is less than 4. Okay, so it is indeed anomalously reduced. Okay, and it in fact reduces sufficiently fast because c grows quite rapidly with swimmer aspect ratio. So if I were to just, so that scaling argument works. So this just tells you that within the range of Peclet, there's reasonable agreement between that prediction and our numerical results, although we might want to go to larger Peclet to be more certain. Okay. So this is one of the last slides. I want to just summarize the result, okay, for axial dispersion, just like I did for shear-induced migration. Okay, so for prolate swimmers alone, I didn't show you the results for oblate swimmers, but rod swimmers seem to disperse in a different manner when their aspect ratio is greater than 2 from the remaining rod swimmers and from all of the disc swimmers. So there is no anomalous dispersion regime for disc-shaped swimmers, but there is one for rod-shaped swimmers where the exponent is lower than that predicted by the classical argument. So that's the encircled result here. And yeah, I think that's about what I have. So I'll be happy to take questions if there are any in the time. Thank you.
Thanks a lot, Ganesh. Very nice talk. So now is Alain raised the hand, Alain Pumir. So you can ask your question, Alain.
No, I was just tapping. That's all.
Ah, okay. Sorry. So anybody has questions or comments? I have a curiosity. Concerning the dispersion, the second part of the talk, I have two questions, two curiosities. The first one is if you know, or anybody in the audience know about experiments with active swimmers in pipe flow where dispersion has been measured, and why, and if this theory somehow apply to these experiments. And the second question is, since you have this aspect ratio dependence on the diffusion coefficients, I was thinking if you can imagine to use a pipe flow to do a sort of separation or selection of swimmers with different aspect ratio.
So the answer to the second question is yes, in the same manner as you would separate it along the gradient direction, because the differences are magnified along the flow direction, then you can certainly separate the swimmers based on this result. Yes. And
thanks.
The first question, I don't know, was it for me or was it for the audience?
I mean, for you or for the audience. I mean, maybe you are known, you know some experiments, or some in the audience is aware of some experiments in which this kind of dispersion has been studied.
So I know that there has been a scaling of Peclet power 4 found. I forgot to include that reference. I think John Wetlaufer is involved in that effort, but it's a collaborative effort. I don't remember all of the authors involved, but that's for the origin of that. They find a Peclet power 4 for the dispersion. So in that sense, it's similar to the classical argument, except that you recognize that the swimmer diffusivity is smaller by Peclet squared, but it's not for pipe flow. It's for a different configuration. I think it's for a porous medium.
Porous medium.
Yeah. But the second, but
is the PNAS paper by Guasto? Is this the one that you're referring to? I mean, or is another paper?
Say that again.
I remember some work of swimmers in porous flow in a PNAS paper by Guasto.
I think so. Yeah, I think so. Okay. But to my mind, I don't know of any other dispersion experiments. There's been simulations by Patrick Underhill of swimmers asking for the Taylor dispersion, but they are for very confined channels. So there is an important question here of in these types of problems, if you have a phenomenon that is driven by boundary effects, or is it driven by a bulk effect? So in all the things that I spoke about, the effect is the bulk. So there is a bulk mechanism that is in operation, and it's not dominated by the boundaries. And that's because I've taken the ratio of the swimmer mean free path to the boundary to be very small. And that certainly was satisfied reasonably in the Roman-Stocker experiments, but it wasn't in the simulation. So I think many of the efforts, especially on the simulation side, the swimmer mean free path is not so small. And therefore, you tend to have influences from boundary trapping, upstream swimming close to the boundaries, and so on. And so it would be difficult to separate those influences from whatever I spoke about. So you need to do it in a sufficiently wide channel in order to
explore the, I see.
Correct, yeah.
Thank you a lot. Thanks a lot. Is there any question or comment in the audience? If not, we can thanks all the speakers of the first morning.